Ferraro. I'm a second-year electrical engineer, and I'm one of this year's co-avionics leads.
I'm Steven Zelazny. I'm the other avionics co-lead this year.
I'm Christian, and I'm a fourth-year mechanical engineer.
This is an overview of our table of contents. We are going to start off going through our details, followed by our analysis, and end with our timelines. To start off, these are our internal requirements as a sub-team. We are going to utilize backplane as a secondary hardware system, and we are going to complete the live video challenge this year, which means we have to implement the live video system and broadcast live video and live telemetry from the rockets. Ezra is requiring that we utilize 2 flight computers this year, one of which must be COTS, and these systems also have to be completely redundant and independent from our tracking systems. The other sub-teams from our IREC have their own requirements of us. Structures is requiring that we have standalone engineering camera systems in both the deployment bays. They also requiring that our avionics bay is less than 18 inches in total length, and recovery is requesting that we send deployment signals to both ends of the avionics bay, since we are using a dual deployment system this year. Our budget includes 4 total sections, the most expensive of which is our live video and featherweight tracking sections, as those are 2 completely new systems to the club this year, so we had to buy them almost entirely brand new. We also have the structural components to build the frame of the av bay, and of course the batteries to power all of our other components. Our total budget ended up totaling just under $1,000.
Okay, so first up, to start with, we have an overview of the avionics bay. It's primarily divided into 2 sections, what we're calling the vertical sled section, which will house our SRAD and COTS components, and then the live video section, which will house the live video systems that we need to complete in the live video challenge, as Emma mentioned. Starting off with our flight computers, we're using 2 independent RRC3 Classics. These are the flight computers the club has used for the last few years, so we know they work and they're reliable. And the primary reason for using them in addition to that is the fact that the club already has them, as well as a lot of backups. So it was made fiscal sense to reuse them rather than spending money on new flight computers. For our primary COTS tracker, we're using the featherweight GPS tracker. And the main draw of it this year is, first of all, it's very simpler to set up and use than the big red Bs we've used in previous years. And in addition to that, it has a feature that allows it to communicate with other featherweights in a sort of mesh, such that if our rocket has already landed and is on the ground, and another rocket launches that also uses a featherweight system, it will be able to ping off the featherweight in the air and still relay its location to our ground station, even though we don't have line of sight with it. Our secondary SRAD tracker is the RS-41 radio sonde. And the big draw of this for us is the protocol it uses, the Horus Binary V2 protocol. And that's because it's a very durable protocol. Last year when it was in the payload, it was routinely transmitted over, and they were still able to decode the packets and get its location from it. In addition to that, the protocol uses a longer transmit time, which allows us to sort of fox hunt it in addition to just decoding and tracking it. For our live video transmitter, we're using the Walksnail Avatar GT. The 2 main reasons we went with this is because it's able to record 1080p 30 FPS video, which is what Ezra would like to receive. And that is a very high quality 1080p 30 FPS, which we think is valuable just for visuals and to hopefully win the live video challenge. The other component of this transmitter that we like is its high transmit power. It's capable of transmitting at 2 watts, which will give us the range we need to receive it while it's in the air. In testing, we found that this VTX produces a lot of heat. And so in order to address that, we have implemented a few heat management systems, the first of which is a cooling system utilizing a fan, which will draw air in from outside the rocket and push it over the VTX, and then exhaust that air out of the rocket to hopefully move some of that air from inside the rocket to outside. The second heat management solution is, as structures mentioned, the top Avionics Bay bulkhead is a solid mass of aluminum, and that will act as just a heat sink for the VTX to hopefully take some of that heat from the VTX. Additionally, and we'll touch on it later, we're going to use a remote activation system to minimize the amount of time that the VTX has to be running. We'll be receiving all these things through our ground station. It will feature an SDR to receive and decode the RS-41 radio sonde. In addition, it will also have its own radio mod to receive and decode backplane, which Emma will get into later. And all this runs on a framework mainboard, which is a kind of laptop. So we are sure it will have the computational power to handle all these things. Our ground station will also be receiving from or processing our live video. We'll be receiving that video through a pair of FPV goggles, which will then be captured with a capture card before being sent to the ground station. The ground station will be running software called OBS, which will allow us to overlay any graphics and the telemetry we receive from backplane before we send it off to Ezra for them to live stream.
As I previously mentioned, we will be using backplane as one of our primary electronic systems in the rocket this year. It's a SRAD system that utilizes 4 modules and that communicate all via Ethernet. We are going to use power mod, radio mod, sensor mod, and deployment mod this year. Sensor mod will record telemetry and transmit it using radio mod back to ground station. Power mod will distribute power to the rest of backplane, and deployment mod will be in there to be tested as a potential flight computer for future years. We are going to have a hardware fuse connected to the deployment signals to simulate an E-match charge, and we are also going to have software on there that will test and verify backplane success at sending deployment signals. We are also going to use backplane to activate our VTX this year. So it will be connected via radio mod to a load switchboard. And as Stephen mentioned, radio mod will be able to communicate with ground station via another radio mod. And a pin on radio mod will be connected to the load switchboard, as shown here. So when ground station sends a signal to backplane, radio mod will activate the load switchboard, which will turn on the VTX. We are doing this so we can turn the VTX on right before launch, rather than having it sitting on, activating and producing heat for a longer period of time before launch and potentially overheating. The engineering cameras are an SRAD system that are completely independent of the Avionics bay. They run on a board called Little Guy that acts as a boost detection system, so that they will turn on and begin recording as soon as the rocket launches. They also have an LED connected to them that will produce light and illuminate the interior of the deployment bays, so we have a better idea of what's going on inside of the rocket before the parachutes are deployed. This is an overview of our entire wire diagram for the Avionics bay. We are going to use 22 American wire gauge wires and primarily use screw terminals and JSTSM connectors. The only exception is a connector that is connected to the VTX that was producer supplied. For our wiring management, we are going to use JSTSM connectors primarily, as I previously mentioned. We are also going to use adhesive batt wiring anchors that will connect to the frame and sleds in the av bay. The wire bundle will be connected using zip ties to these anchors, and then we are also going to use electrical tape in certain places to ensure that the bundle does not come apart during flight. And the majority of the wiring bundle will go up through the center of the two vertical sleds, and from there up to the VTX bay using the side frame of the bay.
So moving into a couple of the more mechanical-oriented details on the avionics bay, just a quick overview of the materials used in the bay. We've got most of the spars, and the majority of the frame is going to be fiberglass, with most of our complicated geometry aligning components 3D printed, and then our sleds and that middle plate visible at the center are going to be Delrin, just to save on a little bit of weight. At the bottom of the avionics bay, we have a spacer. This is to both prevent the avionics bay from hanging entirely off of L brackets on the spars, and to provide a convenient gap for a long wire that stretches underneath the avionics bay to our deployment charges. When you insert the avionics bay into its coupler tube section, that wire needs to have somewhere to go, and so this spacer provides that gap. To prevent incorrect assembly of the avionics bay, we have keyed sleds. So the sleds are different sizes, and if you tried to insert, for example, the backplane sled into our COTS component sled slot, it would not fit properly, and you wouldn't be able to insert the avionics bay into the tube. And also, just to make the avionics bay easier to handle whenever it is not inside the rocket, we have some retention pins at the bottom of each sled to hold them into place once you've inserted them into the frame. So our upper interface with our upper bulkhead is hung off of L brackets attached to the fiberglass spars, and that upper bulkhead up at the top will have those pass-throughs for those threaded rods, which will be chamfered on the bottom of those holes, just to make alignment a little bit easier as you're inserting the avionics bay into the body tubes. On the lower interface, we have that spacer as previously mentioned. We also do need to bear in mind that there's going to be a rail guide inserting through the wall somewhere in the lower area of the avionics bay. And so we're going to be implementing a cutout just around that whenever the location of that rail guide is finalized.
To step back in to talk a little bit more about the spacer and our recovery interface. Since we're doing dual bay, we have to send deployment signals to both ends of the avionics bay, which means we have wires running to both ends and to both sections which have charge drops. Since the avionics bay is a little bit longer than usual this year and we're sliding in over threaded rods, we are hoping to have a longer wire that will be attached to the bulkhead with that connects to the recovery bay, and then we'll also have the other end connected to our own bay, so we can ensure those connections with the wires and the JSTSM connectors before sliding the avionics bay in, and that wire will coil up inside of the spacer to keep it safe and to add a little bit more stability to the avionics bay.
So as with rockets, there are some risks. Obviously we've been talking a lot about the live video overheating. And so that's our first risk here, and we've already pretty thoroughly discussed those mitigations, and we're hoping that with them, which we'll confirm with testing, that we've successfully mitigated that risk. Next. Our next risk is our GPS is failing to transmit, which is an issue we've had in previous years. And we're mitigating this by adding redundancy in the form of using 2 highly reliable trackers in the featherweight and RS-41 radio sonde. And by doing that, we are mitigating that risk. Another risk is if our GPS fails to attain lock. And as I mentioned before, the RS-41, the protocol it uses, has such a long transmit time that you can use it to fox hunt. So even if both our GPS or all of our GPSs fail to gain lock, there's still a method we can use to try and get a bearing on the rocket. There's also some concern about a structural failure of the avionics bay, as we saw last year. And to mitigate that, we're just using stronger materials in the form of fiberglass. And we're also just isolating the avionics bay in between the 2 bulkheads to hopefully mitigate any outside failures cascading into the avionics bay too much. Since we are remotely arming the VTX, there is a risk that that backplane doesn't receive that command to arm, or it doesn't arm for some reason. And to mitigate that, we are going to have the capability to continually send the arm command. And we believe this mitigates the risk because we find it unlikely that backplane would fail to receive all of those arm commands. As structures mentioned, we have some of our vent holes. Obviously, there's the ones for cooling, but these ones specifically are the vent holes for the flight computers, which need vent holes to equalize the pressure in the avionics bay with the pressure outside the avionics bay, as that's how they determine altitude. And to determine the sizing of these holes, we followed the calculations that appear in the RRC3 manual, and we found that the holes need to be 0.316 inches in diameter, and we'll be using an O drill to drill those, which we have confirmed that we have. Now, in making these calculations, we've made the assumption that there's no venting from any of the other holes in the avionics bay, such as screw holes, or the holes that we'll be using to cool the VTX. And in reality, that's not the case. There will be some venting, so we're overestimating the size that these holes need to be, and we're okay with that because there isn't too much of a downside to oversizing them, and the effect of undersizing them is much more severe. As I previously mentioned, we have done some initial testing of the VTX and how it heats in a tube. And the setup for that was we placed the VTX in a section of coupler tube, and we covered both ends with sheets of material. And then we inserted a thermal probe into that tube. And we had a timer, and as soon as we turned on the VTX, we started the timer and recorded the ambient temperature of the air every 30 seconds. We did this test 3 times, first with just the VTX in the tube. The second time, we added a fan to just circulate the air within the VTX tube. And the third time, we added a mass of aluminum approximately equal to the mass of the upper bulkhead, in addition to that fan circulating the air, and the VTX was attached to that mass of aluminum. In the test results, just the fan circulating was marginally better than the VTX on its own. However, when we introduced the thermal mass of aluminum, we found that it drastically reduced the rate of heating in the tube. It's important to note that each of these tests was terminated when we received a warning over the video stream that the internal temperature of the VTX was exceeding its safe temperatures of 9,200 degrees Celsius. So in the future, we are planning to run more tests and acquiring equipment to measure the internal temperature of the VTX so that we can record that, as that seems to be the greater blocker than the ambient temperature.
So just a quick overview of our load path through the avionics bay itself. Of particular note is that That spacer at the bottom gives a nice, a much larger surface than only the L brackets up at the top during boost for the force to act on. The area of most concern is probably those holes through the fiberglass rods at each of the L brackets.
As I mentioned, we did some FEA on the various components. The two components we did it on were the SRAD sled, which backplane is mounted on, and we were concerned about that because it has a large hole in the middle to allow the mounting of modules. However, it was above far whatever we need, so we determined that was fine. And then there's a downward middle plate, which retains the sleds in during snatch force, and initially it was an 1/8 of an inch thick, and when we ran the simulations there was an insufficient safety factor, so we increased the thickness to 1/4 inch and reran them, and we found that it was now satisfactory.
To continue on with our mass budget, the two heaviest components of our rocket are, of course, the bay itself, the frame, and our cot sled, which houses most of our batteries. The total mass of the FA ended up being about 2.3 kilograms. This is an overview of our drain timeline for all of our batteries. Each of the different colors shown has a different battery power in it. We have two trackers, and of course the ground station for the featherweight. The lower section has the live video, and then the backplane and the RC3 flight computers are in the middle. The trackers and the featherweight ground station will all be turned on in the pad queue, and will be turning off after the rocket is recovered. Backplane will be turned on in the salvo queue at the same time, but this will turn off shortly after the rocket lands. The RC3s and the ground station for the live video will be turned on while the rocket is in the salvo queue, and will be turned off after the rocket lands as well, whereas the VTX itself will be turning on shortly before flight, and will be turning off shortly after the rocket lands as well. The engineering cameras are a bit of an outlier, where they'll be sitting in idle state from when the rocket is assembled until flight, when they are activated by the boost detection, and from that time on they will be recording for 20 minutes before turning off after landing. The power budget is an overview of the different batteries we will be using and their capacity. Each of these batteries will be drain tested in the near future. The only one we have tested so far, though, is the RC3 battery, which lasted just over 44 hours before the test was deemed sufficient and it was turned off. Next up is an overview of our data budget. So most of our components will be recording data the entire time they are turned on. The main difference is the engineering cameras, which will only be recording data during the 20 minutes they are recording video. So the main components that will be recording data, though, are the live video, VTX, and the backplane system. This is an overview of our manufacturing plan. The main portions of this include 3D printing our battery casings and cutting the sleds and the rest of the frame of the Avionics bay, and of course soldering and crimping all of our connectors and components for the bay. The steps thereafter are epoxying the frame of the Av bay and putting together the rest of the bay. Our test plan is composed mostly of drain tests and signal and functionality tests for each of our components. The two unordinary tests, I suppose, are the heat saturation test for the live video, which we have already started, but we are going to continue testing in the near future. For that, it will mostly consist of heating up the ambient temperature of the paint booth in the shed to 110 degrees Fahrenheit to simulate the component, or the environment that the VTX will be under while it's in the rocket in Texas. We will then perform the same test that we did earlier to see how the VTX holds up and how quickly it overheats while it's in those conditions. The second test is a L1 stress test for the VTX system. We are going to put a VTX in a similar system into an L1 rocket and launch it at IREC on March 8th, I believe, to see how the VTX holds up under those conditions, to give us a gauge of how well it will perform at IREC. While it is an L1 as opposed to an L3, it should hopefully simulate similar forces to what it will experience in Texas. The main timeline risks are, of course, any components that we order being delayed by shipping and or being out of stock, shed machines that we're going to use to manufacture the bay being down temporarily, and of course weather conditions impacting any of our range tests or the L1 stress test at IREC.